If you've ever waded into the deep end of electromagnetics, physics, or any kind of advanced engineering, you have absolutely come across this symbol, del. It's called the del operator. And let's be honest, it can look pretty intimidating. But what if I told you it's actually one of the most powerful and, believe it or not, intuitive tools you can have?
Okay, so what does this thing actually do? At its heart, this symbol is just a shorthand. It's a really compact way of describing the fundamental behaviors of fields, like how heat spreads through a room or how a fluid flows. Today, we're going to pull back that curtain and show you that del isn't some scary symbol you just have to memorize. It's a powerful tool you can really understand.
So, here's our game plan. We'll start with why this operator is so important in the first place. Then, we'll introduce this really powerful analogy to help you master it. We're going to cover its three main jobs, look at the math in different coordinate systems, and I'll even point out a really common mistake. And of course, we'll wrap up with your key takeaways. First things first, why should you even care about this? Well, because if you study anything that involves fields, and I mean anything, from gravity to electromagnetisms, this symbol is going to be your constant companion. Seriously, it's the key that unlocks Maxwell's equations and a whole lot more. So what is it, formally? The del operator is the vector differential operator. Yeah, that sounds super complex, I know, but just think of it as a set of instructions. It's not a value or a vector on its own, it's an operator. It acts on other things, specifically on scalar and vector fields. It's a verb, not a noun. Now, to really get this, we've got to shift how we think about it. Let's stop seeing del as just another math symbol in a formula and start seeing it for what it really is, a physical tool. I promise this is the core idea that's going to make everything else just click. I want you to imagine you're a surveyor and you've been dropped into some kind of invisible landscape, maybe a 3D temperature map of a room. Your job is to describe what's happening at every single point. Well, the del operator, that's your multi-tool. And it's got these special attachments that can take three very specific kinds of measurements of that landscape for you. So let's check out the three primary functions of this awesome multi-tool. We've got the gradient, the divergence, and the curl. Each one tells us something totally unique and absolutely crucial about the field at any given point. The first tool in our kit is the gradient, and you use this on a scalar field. Remember our temperature map? If you're standing at any point in that room, the gradient tells you two things: which direction gets hotter the fastest, and exactly how fast it's getting hotter. It's a vector that literally points you in the direction of the steepest uphill climb. This image is the perfect way to see it. Think of those V1 and V2 surfaces like contour lines on a map, where each line is a constant temperature. Now, look at that gradient vector delta V. See how it's always pointing perpendicular to those lines? It's not just pointing uphill, it's pointing in the most efficient uphill direction, the absolute fastest way to get to a higher value. Okay, tool number 2. Let's switch gears to a vector field, something like the flow of wind or water. This tool is the divergence. And what it does is tell you if a point is a source, where the field is exploding outwards, or a sink, where it's all collapsing inwards. So positive divergence is kind of like a spring bubbling up from the ground. Negative divergence, that's water going straight down a drain. And our third tool is the curl. This one is all about measuring the rotation at a point. The best way to think about it is to imagine dropping a tiny little pinwheel into a flowing river. If that pinwheel starts spinning, then the field has a non-zero curl right at that spot. It's literally measuring the little whirlpools and eddies in the flow. And what's really cool is that you can combine these operations. Take the Laplacian, for instance. That's just the divergence of the gradient. So think about it. First, you use the gradient to find the uphill flow of the field. Then, you use the divergence on that result to see if that flow is spreading out or concentrating. It's a second-order measurement that really shows you how versatile this multi-tool is. So, we've got the concepts down. Now, let's get into the math. Just like you'd have different attachments for a power drill depending on what you're working on, the del operator looks a little different depending on your coordinate system. Let's call them different workshops. And here they are, the exact formulas for del in our three main workshops: Cartesian, cylindrical, and spherical. Now, don't let all these symbols intimidate you. The job it's doing, finding the gradient, divergence, or curl, is exactly the same. The only thing changing is the mathematical language we're using to describe our position. You can see how in cylindrical and spherical, terms like rho and r pop up to account for the geometry. But the physical principle? That's constant. But, and this is a big but, as we move from that simple, straightforward Cartesian system into cylindrical or spherical coordinates, there is a super crucial detail that trips people up all the time. It's a common gotcha that can lead to a world of pain and errors if you're not careful. And here is the key insight, straight from the source. In a simple grid system, your x and y directions never change, right? But think about a sphere. The direction of radially outward is completely different depending on where you are on that sphere. This means the unit vectors themselves actually have to be differentiated. And that is why in the formulas, you see the unit vectors placed before the derivative. The huge takeaway here is this. In cylindrical and spherical coordinates, order really matters. Okay, we have covered a lot of ground. So let's lock in the most important ideas right now, so you can walk away from this with a rock-solid understanding of this calculus multi-tool. Here it is boiled right down. First, the gradient of a scalar field finds the steepest uphill path. Second, the divergence of a vector field checks for sources or sinks, is stuff flowing out or in. And third, the curl of a vector field measures the local rotation, the spin. Just remember these three words: steepness, sources, and spin. That's the del operator in a nutshell. So, you see, del isn't just some abstract symbol on a page. It's a practical, hands-on multi-tool for describing the physical world all around us. From heat flow to magnetic fields, it gives us the language we need to survey these invisible forces. So now that you have the tool, the only question left is, what fields are you going to survey?